Welcome to the session on the recent advances in big data and social computing. And in this afternoon, we will have 6 or 7 presentations about this topic. So the first one is data relevance table for unstructured data with a focus on unindexed text data. Lu Yang from North Carolina and State University.
As you just see now, function computer, so the function. Okay, so my name is Yang. Our topic is data readiness level for unstructured data with a focus on unindexed data. And data readiness level is a novel concept, and then we define it as follows. Is how ready data is for a specific object in terms of data analytics. Nowadays we have more and more data, so organizations are having more and more on it. And then imagine when you're dealing with data sets as large as terabytes or even petabytes. It is quite computationally demanding, and oftentimes it costs a lot of time. The DRL serves for 2 main categories. First one is for tagging those big name data sets, and then the second one is for large organizations like National Security Agency or those big data companies. They're actually collecting more data than we can imagine. And then when they, oftentimes, they're not indexed. So by index, I mean, say, like your Dropbox, you would have your image files under your picture folder. You would have your PPT files under your work folder. But those companies or organizations like AXA, oftentimes, they just collect huge amounts of data, but without index. And then with the aid of DRL, users can deeply analyze those with higher DRL value, which means the data that are more relevant and more and most valuable. So for DRL, we did it serves for 2 major categories, and one is structured data, another is for unstructured data. For structured data, we had a previous paper published called Towards Data Readiness Level for Structured Data. And for unstructured data, the algorithm and the method used are very different from the structured one. For structured one, mainly we deal with sparsity, missing data, and then the whole process divided from raw data, collected data, and then knowledge. And then for unstructured data, there will be 2 categories: indexed and then unindexed. For those indexed data, it seems easier, right? And then for things mail tend to have a tendency of self-destruction. We think unindexed is kind of more challenging. So for this unstructured data, we did the unindexed part first, and this paper is about that. So next up, the tools that we use include natural language processing kits, scikit-learn, for instance, WordNet 3.0, and the programming environment is Python 2.7. And to briefly introduce WordNet, this page basically talks about 3 things. What is the distance between 2 synsets? What is the depth of a synset? And then what is the lowest common subsumer? For example, banana and grape both belong to edible fruit, and then edible fruit is their lowest common sub-summer, which is the third one. And then for DRL computation, we achieve it by two major figures. One is PKSS, another is PVI. PKSS is percentage of key words and its semantically similar words. PVI is percentage of valuable information. As you can see in the figure, as you can see the figure, it's a 2x8 matrix. So, for example, when the objective is this cat is cute, we first break the phrase into single words. Then it becomes this cat is and cute. These four words are called keywords, and then we calculate its semantically similar words. There are many methods to calculate semantic similarity, but the one we really like is link similarity, simply because it's a value between 0 to 1, easier for normalization. Here's the details of link similarity. And then, as you can see here, as an example, dog with cat. In link similarity, the word dog against cat has a similarity of 0.768, which means dog is a semantically similar word for cat. We denote the set of keywords by big O. So O1, O2, and O3, and O4 in the previous case, that this cat is cute. So O1 is this, O2 is cat, O3 is this, and O4 is cute. And then we use the big upper letter S to denote the semantically similar word set. And then use the upper letter U to denote the union of these two sets. And then the upper letter W denotes all the words included in the title, abstract, and introduction paragraph. And then when the text is very small, like say an email, I probably only have one paragraph or two paragraphs. Then in that case, all of the text in that file is included. So the formula for calculating PKSS is the cardinality of U over the size of W. And then the second figure is TPI, percentage of valuable information. Combinations of nouns, absolute terms, hyperlinks, Boolean values, yes or no, an address, all these, when they combine together, it will lead to valuable information discovered. For example, Lily is 26. That indicates Lily, she is now 26 years old. And then, for instance, a noun plus an address, that means someone's address. Same thing for the number. The second way we discover valuable information is by traditional machine learning techniques. Here we collect 1,000 positive tweets and 1,000 negative tweets. I know the number is quite small, but I'll explain to you why later on. And then we learn its probability of being positive and the word's probability of being negative. And there another important element is called social hotspot. These include Fortune 500 big companies' name, major cities' name, those celebrities' name, politicians, sports stars. When a noun like a social hotspot appears, say Michael Jordan plus something very positive or very negative, leads to a very important information. Say Google bankrupt, it's a social hotspot plus a very negative thing. That means a major event or a very valuable information discovered. And here we denote the cardinality of valuable information. W is the same as we did in the PKSS part. And below that is how PBI calculated. Here is the experiment part. Say when the objective is economics. Oh, by the way, we did experiment by collecting 40,000 PDF files from various databases. Here is a sample of 400 PDF files divided in 4 categories: economics, machine learning, natural language processing, and noise reduction. The reason why we only use the sample picture here is because when there are too many dots, it's really not good for visualization. For demonstration purposes, let's keep the sample size small. And then for the first group test, when the objective is economics, you can see the red dots are having, those files have economics in their metadata or in their keywords. They generally have a higher PKSS value. One can see PKSS value as how relevant these data against the objective. And then PDI value indicates how much information they contain. But here you can see all of the files kind of, except the red dots, all of them are kind of squeezing in the very left corner. That's because they're not really relevant. Say machine learning and natural language processing, they're not really connected to economics. So, and then the right-hand side part is the box plot, and it shows the same kind of result. For the second group, when the objective is machine learning, we see natural language processing as the second highest value. Those blue square spots are those files that have machine learning as its metadata. And then natural language processing is the one that have green triangles. The result is also some, because nowadays natural language processing uses machine learning as its fundamental toolkits. Similar results are shown in the rest of the text. And then to explain why we used we only used 2,000 tweets, here's why. We actually collected around 5 GB of Amazon review to train our classifier. However, the things we discovered is, say, here are good examples. Those images are beautiful, right? These are good and easy to classify. But when for example, the phrase like, the size of the camera is small, and then small normally it is a kind of a negative word, but when it combines with size of the camera, it's actually a good thing. You don't want to carry a very huge one with you for travel. So what we found is we learned those common attributes or common terms in each category. For example, digital cameras. Say there are 100 reviews for this type of camera, the Fujifilm X-T1. And then say maybe 77 of them have sensor size, and then maybe 15 of them have focus as a common term. And then we label them as feature variables, or we call it feature terms. What really matters is the objective followed by those feature terms. Say the camera size is small. Okay, that is a good thing. And then if you look at it separately, look at the score, it's probably low. But if you label it as feature terms, and when they combine together, the results are much better. However, there are many categories in Amazon's data that we downloaded. To see more details, we will, you can see our journal paper. We will publish, we will submit it in this month. And then, thank you. Any questions?